All right, everyone. Good afternoon. We're gonna get started with today's class. So today we still need to finish that open data exercise. And let me just do something quickly here. So open on my side. I noticed that I wanted to have, well, let me ask something first. So in Tifton, is everyone there or is someone missing?
Yes, everyone is here.
Okay, perfect. Awesome. All right. So I want to start off today actually by doing a quiz. I've noticed that I had a few quizzes that I meant to give you during class, but I think I ended up forgetting for whatever reason. So I want to give one of those quizzes right now. So if you go on ELC, I'm gonna make available a quiz for coordinate reference system. This is something we saw maybe a couple classes or maybe a few classes ago. Um, I just made that visible. It's called Quiz 1 CRS. Let me give you a quick timer here to go through it. Oh, it's completed?
It's completed. Completed.
Huh. Does it show as completed for, I mean, have we done this already?
Uh, yeah, we did it. We did it after finishing this chapter, the coordinate reference system.
Yeah, that's interesting because I thought we had, and then I was looking at the grades and I couldn't see them. Did we do the geospatial data types as well? Um, No. Okay. So, all right. So let's do then the geospatial data types, which is one that I would have given you during the video that you watched that day that we didn't have class. So let me
We also did it.
the geospatial data types.
Yes.
I don't know what happened then. Because to me, yeah, I wasn't sure, but to me it says it doesn't show any submissions. Okay, in that case, this is probably something that happened on ELC. I thought I had given, but then I checked and there were no submissions, and so I thought maybe I was going crazy and I didn't give it, but I did already. Okay. Huh. All right, so we're not gonna have a quiz right now. And I'll look into it. I mean, if for some reason, if ELC, I don't know, if it disappeared from ELC for whatever reason, everyone gets 100%. So no worries about your grade. I'm just not sure why ELC would not show me your submissions. So right now it was, so let me make it visible. Maybe you're gonna be able to see it now. Yeah, it's complete. Okay. It shows completed on your side? Okay, yeah, do you have any other quiz that you've done that I don't remember? Yes, CRS and geospatial. Only those two. Okay. Yeah, okay. Well, yeah, I'm sorry for, I guess, my confusion and also whatever happened with EOC. I'm not sure why it's showing no submissions, but again, don't worry, because even if I cannot find your submissions, you're gonna get 100%. Um, it's just I'm not sure why EOC is doing this. Anyways, I guess going back then to our class material, so we don't have a quiz to begin with. Let's go back to our 06 open data exercise. So that's the one that we were working last time. I'm showing you the folder, my folder for the class. I want you to go in the 06 open data, and then as always, launch your rproj icon. That's how we're going to navigate to that. to that script. So once that launches on your side, let me close a few things here. So we were working with this code, this script 0204 open data partial. If you're not seeing that, well, always make sure you are in the right project. So you should see 06 open data on the top right. And then on the files tab, you can navigate your code and then just click on your 0204 open data partial if you're not seeing that. All right, so last class we talked about some APIs. We talked about using USDA NRCS Sergo data for soil data that we have access here in the US. We saw that it was a very extensive data set that you can get data for a given field and get a lot of information for whatever soil series you have in your field. We talked about elevation data, although we did not pull open source elevation data at that point. And then we talked about map components. So I'm just going to go here and play each one of the chunks. There's one of them that if you go beyond what I'm showing, there is one chunk I don't want to run. That's the one that we print the Sergo data frames. It takes maybe a minute to run on my side. So I don't want us to get stuck there. But I'm going to run the boundary one. I'm going to run the soils again. So this is going to pull that soils data. Oh, I think this was the one I did not want you to print. So too late on my side. If you have not, you do want to run this first part of the chunk here where we download the data. And if you end up printing, that's fine. I mean, it did not take a whole minute, but it took a little longer. But anyways, after you run this chunk, we get the data from Sergo. We talked about different components. There's a spatial and a tabular component within that object. So we played a little bit with them. We made some maps. I'm not going to run this chunk. We're not creating anything here. We're just exploring. So I'm going to move on. Then we discussed about the three of those components. So one is called components. One is called MU aggregated. So MU is mapping units, and then mapping unit crop yield. So we play with that. We did this wrangling here to join the spatial and one tabular component, in this case, the mapping unit aggregated component, basically bringing the polygons of the soil series of that field with one of the tabular data frames that come from Sergo. So we took a look at that using map view. We create a map view coloring the polygons by the mapping unit name, which is that full series name with information. So it has the series name, it has the overall texture, and then the percent slope of the series as well. We made a static map. Oh, hold on. I should actually be running the. So we need to run the series SF chunk just so we create that again. We made a interactive and a static map as well. I do want you to run the series map chunk. I do want you to create this object here because we're going to be using that in a second. Then we created another object here that, if you remember, there was that tabular component called MU crop yield. So we join again the polygons, the spatial information with that tabular data for crop yield. And there were a few different crops there, data for a few different crops. We just filtered by crop equals corn. And then we created both an interactive map like this and the static map. Make sure you run the static map chunk because we want to have that object for the next part of the exercise. And this is where we stopped last class. So I just want to take a quick moment and ask if everybody was able to get to this point, if anyone needs some help, and so on. All right, so let's move
All
on.
right, real quick. We just unmuted. I did run into an error, but I'm gonna go back and try and fix it. But it was just I'm trying to find where it was. Sorry, it was in the series F chunk. It just gave me an error. But I'm just gonna close it and then try again. So
Yeah, I mean, if you, I mean, sometimes closing and reopening helps, but if the error message is informative, maybe, I guess maybe try to.
it's st underscore crs uh, parentheses x set equal to st underscore crs y is not true. I don't know if that makes any sense. I don't really understand it.
Yeah, okay. So what that is saying is basically saying that the CRS, so the coordinate reference system of what is coming from the left, which is soil spatial, it's saying that that is not the same as what is coming on the right. Or, well, now looking more closely, I don't think it is here. I think the problem is happening at your ST intersection. So it's saying that the CRS of soil spatial, so I'm going to print that here just so we look at it. So soils $spatial has a WGS84 CRS, at least on my side. I think it does on yours as well. And then boundary also has WGS84 on my side. So I'm guessing that on your side, Luke, maybe for some reason, I'm not completely sure why, one of your CRSs, either from the boundary or from the soil spatial, is not WGS84.
Okay, I see. I'll try and fix it, but then you know, I'll see if I can figure it out.
It's kind of interesting because, yeah, I'm not sure why that would be the case because we did not change the CRS of anything at this point. So maybe, if you want to check again, you can just print, but I mean, I'm back at the chunk where we imported boundary. But if you just print boundary and you look on the first panel here, you can check what is the CRS. Is that WGS84 on your side?
Sorry, no, I just opened up the project file again. I'm having to reload the library, but I'll check and I'll tell you.
Okay.
You
Yeah.
said boundary. Um, let's see.
Well,
No, it's WGS84.
so boundary is WGS84.
Yeah.
Okay, so as you keep moving here, so if you reopen everything and you did not save your environment, which is what I recommend to not save your environment from one to the next RStudio session, then you're gonna have to run the chunks that create objects. So the soils here is one that you want to run again. So once you run that, you just keep going. You're gonna have to, I think the next chunk after the soils chunk, the next one you have to run is series SF. So try to run that again. I think this is where you were getting
It worked this time.
Okay, awesome. Yeah, so again, I don't know why that happened, but the error was basically saying that the CRS of soil spatial was not the same as the CRS of boundary, and that's why it was not letting you do the intersection. This happens when when the CRS of different layers that you're using together are not the same. The CRS is not the same. In this case, I'm not sure how that happened because we never changed the CRS, but it's a good reminder for us to not save our environments from one session to the other, right? So when I close this RStudio window, so it closes, I don't want to save my environment. When I reopen this project, I do not want to see these objects here when I just open the project, right? Because those are like ghost objects. They're coming from the past back into your session, and that can cause problems. If for some reason you did something to one of those objects last time and you forgot and you did not include that in your script, now that you reopen the project, if those objects come back with that change, we don't know what happened, right? So remember that if we have the code and if we have the data, we will be able to recreate all those objects. So we don't have to get attached to objects, right? We can just let them go once we finish. So just a reminder for all of us to to not save our environments when we close our studio. We definitely save your data, definitely save your code, your script. Do not save your environment. All right, anyone else need some help before we get started with elevation? All right, I don't hear anything, so let's get going. So our next open source data API that we're going to be using here is going to be to pull elevation data for our field. So what we're going to do is, if you come on here in this chunk, we give the assignment symbol. We're going to use the function called get_elev_raster. So this is a function from the elevator package. We give it the boundary. So it is called boundary, right? So we don't have to worry about it. It's just the name of the object that we've developed. We created this boundary, if you remember, from the previous exercise. And then this function here has an argument for z. So z, I want us to try 14 first. So what this is basically if we ask for help of the get_elev raster to check what are the arguments available and what does z mean, you would see here that z is going to be the zoom level that you want for your elevation data. So there's going to be different resolutions of elevation data we can get, and z controls for that. So we just want to say that we want the level 14, which is the highest spatial resolution we can get through this function. So if you run this, it's going to basically download, and it's going to give you a message, something like this. If you print elevation object, right now it is a raster layer, which is a type of object from, so if you remember when we work with raster objects in R, we are going to use the stars package, which is kind of like a sister package to SF. SF for vector data, stars for raster data. There is also a package called Terra, which is another package in R to handle raster file or raster objects, which is what this elevation right now is in Terra format. One of the reasons why I like stars is because it plays well with ggplot. If you try to plot this elevation data using ggplot right now, this is not a data frame or is not in a data frame format. And so ggplot is not going to like it. Because of that, I want to transform this to stars. So if we give it a pipe, I'm going to connect this to a function called st_s_stars. Every time we're trying to transform a data frame of some type to a raster and that raster to be as a stars object, we wanted to use the function st as stars. If you run that, it is going to download again, but it's very quick for this field. And then you can print this elevation object again. Notice how now it looks, when we print it, it looks different. This is how a stars object prints. So if we come on the first panel here, it has maybe a couple similarities with SF when we printed. So it's telling us it has 2 dimensions and 1 attribute. The 1 attribute here is basically the name of this attribute on the data frame of the stars is this ugly name of file A something. Really, I don't care much for that, but this is the elevation data. And then it gives us a statistical summary saying that the minimum is 41, and this is in meters. The maximum is 47, almost 48 meters. So there's a good elevation. Oh, I'm sorry, the maximum is 52, not 47. I was looking at the mean. So minimum 41, maximum 52. So there is a good gradient in this field, right? So about 10 meters gradient in some direction that at this point, we don't know what that is. Because this is the first time that we're looking into a stars object, I do want to walk you through a little bit more of how what are the information we get when we print a stars object. So if we go here on the second pane, it gives us this table here. So it's saying that our dimensions are X and Y, and these are just like coordinates within the array. So this is going to be, raster is an array, and I'm going to talk a little bit more about why that is. So the delta column here is basically showing us the resolution. So this is basically 3.99 or 4 meters in resolution. It's not a very clear way of showing it, but that's how it shows. And then it's telling us that the reference system or the CRS is WGS84, and just gives some more information. It's not, so I have to admit that a stars object is not as friendly as an SF object, or at least is not as intuitive as an SF object. However, SF is for vector, stars is for raster. They're two different file types. So that's what we're going to be working with. Okay, I want to show you, let's see here. Yeah, so let's come to the next chunk, and I just want to make a quick map view of this object called elevation. All right, so this is the elevation data that I have, that we all have probably, right? If you just toggle that off, it did not turn off actually for some interesting reason. But our field is right there in this elevation. I think it's just kind of slow to toggle on and off. But you know, what I wanted you to realize is that this is a whole tile. So a tile is basically a piece of that information that comprises your field, but is larger than that, is the tile that they produced for this region here. So our field is behind this, but it's really just a portion of where this tile is. It's not the whole thing. So with that, what I want to do is I want to clip this raster to our boundary. We've done this before with the soils data as well. I want to clip this raster to our boundary. So let me see, where do we do that? Yeah, we do it right here. So if you just come back to this chunk here, let's give it a pipe. And if you remember, so this is interesting because before when we had, this is a great point, and I don't know if I actually mentioned this last year when I taught this, but notice the difference here. We have a raster, that's the elevation data, that we want to clip. So imagine we have a cookie cutter of our boundary, we want to clip that, right? To only have our field elevation data and nothing that's outside the field. So we have a raster, we're clipping with a vector. Our boundary is a vector, right? So raster and vector clipped. We're going to use st crop. And then here we're going to say boundary. So our cookie cutter shape is the boundary. We're cropping the raster with the boundary. So if you run that, and now you redo your map view, it's going to be just for our field. And it renders a lot faster as well, you can see, because now there's less data, right? Okay, so a couple of things here. Here on this chunk above, we had a raster and we cropped that with a vector. And so we use the function stcrop. I'm going to scroll up on my script. You don't have to on yours if you don't want to. But when we did that with, so I'm bringing here the EODSF, which is this here. So EODSF, we started with a vector, right? So soil spatial was a vector. We had polygons. It was not a raster. And then we wanted to clip also that soil spatial to our field, which we did right here. We used the function st_intersection. And you may ask, why didn't we use stcrop? Because we just used stcrop for the same purpose, now with elevation data. The difference here is that when we did this cropping to our field for EOD SF and for series SF as well, if you go back to that chunk, we use the same function as T intersection. In those cases, we are clipping a vector file with another vector file. So ST intersection is when you have two vectors that you're clipping one with the other, right? You are intersecting them. And when you have a raster and clipping that with a vector, then we use ST crop instead. It's just a difference in nomenclature and how the functions operate. But just so you get this understanding that raster with raster, if you want to clip, it's called ST intersection. I'm sorry. Vector with vector is ST intersection. Raster with vector is ST crop. All right, so we crop to our boundary. We can see here, and I do want to really call your attention to, I think this is a great point to explain one of the differences between a raster and a vector, because sometimes this concept may be a little bit difficult to really grasp. So I do want to take a moment to talk about that right here. So vector, if I have a vector of, let's say, a polygon, like we have here on this field, and we're just going to go back up here. So all these soil series, before we did the ST intersection, we had this whole map with soil series, not just our field, right? We had a whole map. And then we did an ST intersection, and then we just kept the polygons that intersected with our boundary. Close my email here. So a vector file, so a polygon type of file or object, when you clip it, you can have empty spaces. You can have holes, right? Imagine that if this field had a hole right in the middle that we delineated, we digitized the hole would be there, and there's nothing wrong with it. It's gonna be, I guess what I'm trying to say is it does not have to be continuous throughout the whole bounding box of that object. On the contrary, a raster object has to be continuous, even if you crop it. And you can tell that here because you're still seeing the bounding box around this raster. And the reason why you're seeing that is because when it did the cropping, all the raster cell values outside of the boundary became NA. However, the cells are still there. You cannot remove the cells. You cannot have a raster that is irregularly shaped. It has to be rectangular, always, even if your shape inside of it is not. So really what's happening here is all the cells inside of our boundary are there, and they have a value in those cells that represents elevation. All the other cells outside of the boundary, because we cropped this raster to the boundary, those cells are still there, but they have NAs. So the cells don't go away. They just become NAs. On the contrary, with the vector, you don't have cells, right? We have shapes, and those shapes can be of any form or shape or anything like that. So it's okay for something to not be contiguous or to not be rectangular if it is a vector. So that's one way, I guess, to think about, how these data are stored, right? So vector is stored as part of a shape, and then data associated with that shape. And that could be a polygon, could be a line, could be a point. On the other hand, we have raster that does not have shapes. It has cells, and the cells are all the same size. And inside those cells, there are values. And even if there's no value in that cell, like if there's an NA, like in this case here outside the boundary, the cell is still there. It still exists. It just doesn't have any values in it. But this was, I think, a good way of showing the main difference. Also, something that's going to be interesting, you're going to notice on the future exercises, is you can start with raster and transform that to vector, and the other way around as well. It just changes how you are using and storing that information and how that's going to be computed with different algorithms. But you can do that back and forth if you wish. Any questions about this concept? All right. So Okay, so we clip this. This is pretty much what I want, but I just want to show you what happened. So maybe on your side, keep it like this. On my side, I want to show you here, if I were to come to this get elef raster function and change the value of z. So I think 14 is the maximum, but I can go lower. If I decrease z, our pixel size increases. So let me change on my side to 13 so you can see what happens. And then I'm gonna show on my view here so you can compare. Can you notice that it became a little bit blockier compared to yours? Maybe it's not as dramatic, so I'm gonna decrease even further. I'm gonna put a 10 here. And then plot it. See how it's becoming blockier? So as you decrease the number z, it increases the pixel size of the elevation data. Really, I mean, I try to get the best data possible. So 14 is going to be the smallest pixel size, so the most information, but you can play around if you need to. Awesome. All right, so this is our elevation map. Let me, since we can play around with this, let me change to S3. I don't know why when I change it's disappearing. Not sure what is going on. So let me try to maybe force my map type to be S3 from the beginning. Okay. Yeah, so for some reason, when I was changing on the go here to S3 world imagery, my elevation was disappearing. I just forced map type to be S3 world imagery as a default, so now I can see both. No, I don't know. Is anyone having the same behavior? Okay.
Yeah, I'm seeing the same thing.
Yeah, it's the same.
Yeah, I don't know why. I mean, something may have changed on the package versioning that is doing that. It didn't used to do it in the past, but yeah. But anyways, so this is, if we just take a quick look at this field here. So this is a grower's field. If you had to interpret this map, this elevation map, what would you say about it? Let me ask somebody online. Polly, what do you think? How would you interpret this elevation map?
In my understanding, I would say that part in the violet color, it's a little bit sloppy, and if there will be like a deposition or soil erosion, things will be moved to that color in 54, the less elevated.
So where is the highest point of this field? Where is the lowest point of this field? What do you think?
Now I see the region. I think it's the opposite thing of what I said. The region in the 54, if you can see the number 54, the color correspond to 54, will be more elevated than the color in deep violet.
Right. And awesome, perfect. Thanks, Polly. And now let me ask perhaps Aman. Aman, given what Polly said, so yellow on the left side, on the west side, is higher than purple, right? So what would you expect for water to do in this field when it rains or maybe when they apply irrigation?
So the yellow point is like highest, so it's like more elevated. So water will flow the opposite.
So can you use like cardinal directions, like water is gonna flow from this to that?
From 54 to 47, like
From west to
west
east,
to-
right? West to east, yeah,
Yeah.
north, yeah. So from left to right, I guess,
Yeah.
right? Yeah, I agree. This information here is really useful, and you're gonna see that in a moment when I give you a new assignment. So to tell the truth, I was designing a study that we're gonna have on a field here in Watkinsville. And I was designing that study this week, and I did pull Surgo data, elevation data to determine where I would place my blocks. So the reason why I'm showing you these, first because soil series and elevation data are really important in agriculture, right? I mean, we know that these two layers can have a big impact on yields and explain yields to some extent. But also for experimental design purposes, right? If you had to design a study, then you can try to place your blocks and plots within one of these elevation gradients if possible, right? To minimize the effect of elevation in your study. And this is data that you don't even have to go to the field to get access to, right? You already can get this from a line of code. So it's really helpful for us when we're, both planning our studies, but also when you have your data already, you want to see their correlations, you can also apply for that purpose. So this is how at least I use these types of open source data. Okay, so the next thing here is I want to create a static elevation map. So let's do this together here. We're going to start with ggplot, as always, with the static maps. Let's add a plus. Now, you don't know this yet, because I think it's the first time that we're using a stars object. But we talked about last class. I asked you all this question of last class, we had an SF object, a vector object. What was the geom that we would use to map that? I don't think anyone was able to tell me if I remember well, but that was geom SF, right? Geom SF is a special geom in ggplots just for plotting SF objects. Very similarly, there is a geom stars to plot stars objects. So let's go ahead and call geom underscore stars. And really all we have to say is just data equals the data frame name, which we named elevation, or the object names. So if you run that and you print it, this is what it gives us. So there is one thing here that is intriguing to me, which is the fact that this map here does not look like our field, right? It's kind of distorted. For some reason, geom stars does not set your y and x axis according to the actual proportion that they have in space. There's a couple ways we can fix that. One of them, if you give it a plus, is to change the coordinates to chord underscore equal. So this sets the x and y coordinates to have equal extent. So if we do that, now this fixes this problem. Another way to fix this that I want to show you, so I'm going to comment off the chord equal, is for you to bring in here a geom SF. So let's say if you have the boundary, we could call geom underscore SF, data equals boundary, and I just want to make the fill equals NA so we can see through. And then you can map it. So for whatever reason that I don't know why the authors of these packages, so really the person that created stars for raster and SF for vector is the same author. And for some reason, when that person developed the SF package, they made it so that when you use geom SF, it already sets your coordinates to be coordinates equal without you having to change. But when you use geom stars, that behavior is not there. So you have to fix that by either bringing a geom SF that makes sense for this field, in this case, the boundary makes sense, or by changing for chord equal, like we did on the first attempt. Okay, so I'm gonna delete the chord equal here, but that was just for your knowledge. All right, I want to change a few things here. So one of them, as always, I will change this color scale to be colorblind friendly. We're gonna add a plus, because even though we did not have to say here on the geom stars that the fill equals elevation, and really we don't even have an elevation column in this elevation object, then this is the name of that column, I guess, which is not a really friendly one to type. But even though we didn't say what was the fill, one of the other differences between a raster and a vector is that most of the time, a raster is going to have one column only. It's going to have all those cells in this matrix with one value per cell. So in this case, that one value is elevation. On the contrary, with vector data, like the boundary or like other things we're going to see, you have the shape. So let's say the polygon of the soil series, and you have many columns associated with that same shape, right? If you remember here from when we did everything that we did here above on the yield SF and the series SF, there were many columns on these data frames. There was not just one column. Whereas with raster, even though it does not show a data frame for us, but it only carries one column inside of that or within those raster cells. So because there's only one column, then it basically assumes you want to fill by that one column. That's what it does for us. Yeah, all right. So let's change this fill because it's the fill of those cells that we're going to change. So it's going to be scale underscore fill. I want to use Virides. We can use here C for continuous. And I do want to change the option for option uppercase B. So this is how that looks like. All right. Also, I want to change this this legend title because right now it does not mean anything. It's just what we got from the elevator package function that we got elevation data from. So I'm going to come here, add a plus. We're going to use the function labs. And this specific lab here is for the fill lab legend. So we say fill equals to elevation in meters. Oops, let me show there. Finally, I want to do two more changes here. One is I want to use a theme that is a better theme for mapping, just because of the settings of the theme. So I want to add a plus and call theme underscore map. That's the one that I'm looking for. As you can see, it makes things a little bit cleaner. It removes the X and Y titles and levels and all that. However, it does place our legend kind of on top of the map, which I dislike. So I want to fix that as a last thing. So if you come here, let's add a plus. We're going to call the function theme. So just a quick heads up here. So if you want to choose a theme that changes a lot of things, that is a preset theme with a lot of things that you like, you would do that by doing theme underscore and then the name of that theme. Like we did here, theme underscore map. However, if you want to have control of something very specific about the theme, for example, placing this legend in a different place, even if you call a theme underscore something, you cannot change that something specific inside theme map in this example. You have to call the theme function alone, and that will give you access to all the options that you can change. So I want to change here something that's called legend.position. I want to say right within quotation marks. So this is how that's going to look like in the end. All right. So now the last step that I want to do here is to combine all these three maps that we made, all these three static maps that we made, and export to file. So one way that you could combine these is you could export to file each individual map and then open PowerPoint and then move each one into PowerPoint, align them, and do things like that. Could do this manually, and maybe you've done something like this in the past. I want to show you here a very powerful package that is called Patchwork. So patchwork, I think I'm gonna go to our first chunk here on the setup chunk. So we have already loaded patchwork, so we don't have to load again. So I'm gonna come back to that combining and exporting. So the way the patchwork works is intuitive as well. So we basically say, if you notice, starting here with the, let's see, static series. So we made this static series map and save or assigned that plot to an object called series map. The same thing we did with static yield, which we assigned to yield map. And finally, with elevation that we assigned to elevation map. So now we're basically gonna call back those objects in sequence and join them into one plot, side by side. So let's begin here with the series map. So series map. We're gonna add a plus here and call yield map. And I just wanna run at this level, just so you see what happens. So if you run this, this is what we get. Right now is looking kind of like weird because we have not saved to file yet, but when we do save, I think it's gonna look better. One thing to point out is even though we're adding a plus in between them, and it looks like a ggplot plus, really this specific plus sign is coming from patchwork. If you do not load patchwork, just ggplot2, and you say this, it's not gonna work. Or when we add a plus here and it looks at the object types of both objects, and if they're both ggplot objects, then it uses the plus from patchwork and not from ggplot. So just to keep that in mind. So finally, we're gonna combine these two. So add a plus with elevation as well. So elevation underscore map, and you can just run that. So you would see both all three plots side by side. Again, right now they look very bad, and that's because we have not saved them to file yet. So maybe let's save them to file just to check how they look like. So I want to call a gsave right here. Gonna give it the quotation marks, get outside of the code folder, go inside the output folder. I want to call this combined underscore map dot png. We can run that and see what happens. It's telling me that it's saved on a 7 by 7 inches map. So if you go here on the files tab, output folder, looking to combine map, this is at least how it looks like on my side. Pretty ugly, right? We still have to do some adjustments for this to look like a nice output. One of the ways we can make it look nice is just change the dimensions that we're saving to file. So I would come here on gsave. It has an argument for width. I played around with a whole bunch of numbers and I found one that looked good. If you don't, like if you're doing this on your side with something that's related to your research and you don't know what looks good, you're just gonna have to do some trial and error. But that's how I found out the width of 12 inches and height of 8 inches worked for me. So run again the gsave and then go again on files, output, combine map, and check it out. This is how that looks for me. Better, right? So we can see the maps better. We can see the legends. There's nothing overlapping with anything. So really nice. We have our north arrow and scale on the first plot. Because these maps are all from the same field, it is sufficient to only add on the first one. But if for some reason you wanted to add on all of them, you have the code of how to do that when we did for the first one. Okay, so I think I want to show you a couple things here. Yeah. So if you ever have to merge different plots in different ways, I highly encourage you to look for the package patchwork on Google. they have a great vignette that really explains. We are just using the plus function here. They have so many functions. You can organize these plots in so many different ways. You can put them under each other. You can put two on top, one on bottom, one on top, two on one on top, two on bottom. It's really like you can do a lot of different ways of combining plots. It's very, very powerful. So if you ever need to combine plots, I'm gonna leave this advice for you to check the patchwork vignette on your browser. It has a lot of great examples, and you're gonna find a lot of resources there. One of the functions that I'm going to show you here, one of the many functions that Patchwork has, is you can annotate this final plot, right? So I could have, for example, I could have added a title specifically to series map, title for yield, and a title for elevation. But now that I combine them all together, I want to add a title to that entire combined product. We can only do that after combining, right? So I want to give it a plus here. I'm going to break line just to make it more readable. Patchwork has a function called plot underscore annotation. That's what we're going to use here. One of the things I want to change is the title. So I want to say title equals to, I'm going to write a title. I want to write soil series, and then in parentheses A, corn yield, in parentheses B, and elevation, and in parentheses C. If you run all that and you run the digisave again, it's going to be easier if you export to file and check on your files rather than in R. But then open that map. Now we have this title here, soil series A, corn yield B, and elevation C. Right, so if you're sending this for a paper, publishing on a paper, you have to have your different elements here with A, B, and C, right? So this is how I would at least give a title saying A is soil series, B is corn yield, C is elevation. However, that is just the title. The actual A, B, and C letters are not appearing yet on our plots. Again, you could do this manually. You could bring this into PowerPoint, add them yourself. Life goes on. I want to show you how we can do that with this function plot annotation, and doing so is going to do automatically for us. So right after that closing quotation mark, give it a comma and break line just to make it more readable. Plot annotation has an argument for tag underscore levels. So here I want to give quotation mark A, so it knows that it's going to do ABC all lowercase. If I give A uppercase, it's going to be ABC uppercase. If I give a number 1, it's going to be 1, 2, 3. You can learn more about other ways you can specify your tag levels by checking the help function on the plot annotation function or on the patchwork vignettes that I was telling you about. If you run this, and you export it to file with digisave, you can check your output, you can open that combine map, and now you have an A, B, and C on your facets automatically. Something else you can also do is change the suffix of this tag. So if I add here comma, it has an argument for tag underscore suffix. I want the suffix to be a closing parenthesis. If you run that and you again export to file with digisave, go to output, open combine map, notice that now is A parentheses, B parentheses, C parentheses. There's also another argument for tag prefix if you want something before the lettering. So there's a lot of ways you can customize this. I just wanted to show you a few of them. All right, I think this is sufficient for this. Any questions about what we've done? Was everyone able to do it?
Is there a way in the raster map, in the elevation map, to have a white background for the NA points instead of a gray background?
Yeah, was that Mohit?
No, it's Marco.
Marco. Yes, Marco. Yes, thanks for that question. Okay, so Marco is asking if there is a way to make the NA cells white. Yes. So the way that we would change that is basically coming here on the scale fill varieties. I think every function that is scale fill or scale color is going to have this option. Let me see here. I think it is NA value. So NA value, let's say white. I think this is what we need. Let's try that. Yeah, that's what we need. So on the scale fill varieties, you just say NA value and then give them the color you want them to be. So make sure that you run this on the elevation map chunk and then run again the combining chunk, and that effect should trickle over. Yeah. Nice.
Okay.
Very good point, Marco.
Thank you.
All right. Any other questions? Okay, so let me see here. Okay, I think that wraps up this exercise. So very quickly here as a summary, in this exercise, you learn how to pull data from two open source APIs. One soils that was from Sergo, another one was elevation, which is coming from, I think it's a USDA source as well. We created maps for those different variables while adding these map components, and then exported to file a combined map, right? So again, a lot of times, again, I was telling you earlier that when I'm planning a study, I always use these types of resources to learn about the site that I'm going to do a study even before I do it. I think it's very useful. I've been using this a lot, and I find it very useful. I hope that you may also apply something like this to your own study sites, and find out more about them. All right, I'm gonna save my script here, and I guess I can leave this RStudio window open just because I want to show you something. We have an assignment. So if you go, let's see here. I think you should already have this. If you don't have, you're just gonna have to download again 2025 PPA. But from last time that you downloaded, I think this assignment was already there, which is this assignment. So I went into 2025 PPA inside of the 02 assignments folder. There is an assignment 04 open data. So basically I'm going to launch this script. I think it's going to open right here. But basically what I'm going to ask you to do is to repeat some of the steps you did in class to digitize a field boundary, to pull Sergo's data, make those maps, pull elevation data, make that map as well. That's the overall goal of this assignment. But I'm asking you to do that for a field of your interest. So if you have a field trial, if you have trials out somewhere in Georgia or elsewhere, I want you to digitize that boundary. That's what I want you to bring here, and then use that boundary for your field where you have research and pull Sergo data, elevation data, and then create those maps. I have some instructions here that are more detailed. We're going to go through them. So basically, once you download this assignment 04 open data, I want you to copy this from the 2025 PPA folder and paste this inside of the code folder of 06 open data. So the same project folder we've been using for this class exercise, I want you to paste that script, that assignment for open data script inside the code folder of 06 open data. That's where it should be. Do not just double click on the one from 2025 PPA and work from that one. Don't do that. So once you move this script here to your 06 open data code folder, you can open it there. I have some instructions for you here. So asking you to move this script to your to the code subfolder of your 06 open data folder. You do not need to create new scripts. What I want you to do is basically work on this assignment 04 open data script, bring the code you need in here, and this is where your coding is going to happen. You are welcome to use the other scripts that we have done for digitizing and for the open source that we just finished. You can use them, no problem. You can copy those chunks and paste them into this script, but I want you to do everything in this script here. I left you the scaffolding of the structure of this exercise. So you can look for that on the outline on the side. Make sure that you do not delete the structure I left you. Whenever you are answering a question and you're copying code from the class scripts into the assignment script, I want you to basically paste those code chunks where they should go. And what I mean by that is, for example, I left you here a setup function. Under the setup is where you're gonna load your packages and bring in any data if you have to. Under the digitizing section is where you're going to digitize, right? So I want those chunks to be in the right place according to this outline that I'm giving you. Let's see what else. So besides your code, I also have actually 5 questions, not just 3. So that was a typo on my side. I have 5 questions for you that I want you to create what you need to answer and then actually answer them as text. Do not just give me the output. You're not going to get full credit for it if you do. So I want you to write down the answer to my question. Okay. So a quick overview of what I want you to do. I have some introduction here. Basically, I want you to digitize a field boundary for a field of your choice. If you have research field, do it for one of your research fields. If you do not have a research field, let me know. I can provide you with another field for you to work with. But yeah, so it's going to be a field not the same as the one in class. That's the main key thing, is that it has to be one different from the class field. Then I want you to retrieve open data related to soils and elevation for that, and then create plots to explore it. So again, you're going to find a field of your interest, and then do this exercise for that field. So for example, I have a question here. Question 1, provide below the longitude and latitude of the centroid of your selected field. Remember, this is something that the way that we start digitizing is with that centroid. So I want you to give me the centroid right here. You're going to do the setup. You're going to do the digitizing. Now, the digitizing, I have a note for you that's really key, that we have a lot of issues last semester, and I want to clarify this time from the beginning. If you remember, there's maybe 3 different chunks that you're going to use for digitizing. One of those chunks creates an active, interactive window for you to do the digitizing. The first time you do that on this script, I do want you to have all those chunks active and working in the script so you can actually do the digitizing, right? If you remember on the digitizing exercise, after you do the digitizing, we export that boundary to file. So on this script, I want you to have the code for digitizing, and I want you to export that to file the first time around. I'm saying this because the way that you're going to submit this script here is going to be by rendering. And if you render and it has that active digitizing code, it's not going to work. So the first time you do this, you have the active codes, you export that, you do the digitizing, export that product, the boundary to file. Then once you exported that to file, I want you to comment off those pieces of code of those digitizing chunks. So all the digitizing chunks and the right SF chunk exporting to file, I want you to comment them off. And below that, once you have done the digitizing, I want you to then import with an active code that will be active when you render. I want you to import the boundary that you digitized the first time. So when you render, when you're ready, when you've done everything, you're ready to render and send to me, your digitizing code will be there, but there's going to be a comment in front of them. So they're not going to be interpreted. The only active part of that is going to be the read SF that you do to bring back in the boundary that you digitized and exported. I know I said a lot of words here. I just want to take a quick moment to make sure you all understood what I described. Did that not make sense to someone, or anyone has any questions about that? Right, I'm not hearing anything. If when you render to submit, you run into an issue, maybe that is the reason why. So just wanted to clarify that.
But can we use like a GIS software to do the boundary if you know how to use that? Or is it mandatory also for that part to be in a... Because all the issues that I ran the last lecture, I discovered that was because of my boundary. So I redid it with GIS and then everything goes straight.
Okay, yeah, I'm not, so you should be able, I mean, if you have a very complicated boundary, like you have holes in the middle and you have things going on, it may be easier to do in a GIS like ArcGIS or QGIS. If you have a boundary that is mostly like rectangular or approximately rectangular like ours, then I think you can try here. So I guess what I would say is try to do as we did in class. If you have issues, we'll try to figure that out. And if it's still giving you issues, then I'll accept from another GIS. I'm not saying this mostly because if you do on another GIS, I don't see what you're doing, right? And I do want to make sure that you all can demonstrate to me that you're doing that. And so if you have the code here, I can see that you did in a better way. So yeah, I would propose that we first start doing the way we did in class. And if that doesn't work, then, let me know, we can talk about it, and then we can make some exceptions if needed.
Okay.
Awesome. All right, so once you digitize the boundary, export to file, then you bring that boundary back in, right? Remember, when you render, the rendering is not going to digitize for you. So you're going to have to render, reading that boundary back, and then you do the rest of the exercise. So soil series, I have a question too here related to how many soil series you found in your field. And this is also a question that came up last year. So not every field or not every soil series is going to have yield data for corn. Perhaps there are some that have yield data for no crops. I don't know. But I'm asking you here to choose one crop. So when you do the soil series, and you're going to see how many crops you have yield data for. Maybe corn is not going to be there. We looked for corn in our in-class exercise. If you don't have corn in yours, but you have another crop there, choose one of those available crops for your mapping unit, soil series map. If there is no data for no crop yield on your field, then just tell me that there was no yield for no crop, and then that's the answer, right? All right, then I ask you to pull elevation. I'm asking you to combine and export those maps, just like we did in class. And then I'm asking you this question. Now that you can visualize all three maps together, try to explain the effects of soil series and elevation on crop yield. Which soil and elevation conditions seem to promote higher yields in this field? Of course, this yield data that we're getting from Sergo is not very reliable, right? It's probably a number that I'm not even sure how it was determined. But if there is a pattern there that you can identify, tell me about it. If you see no patterns at all, you can answer that as well. But I just wanted to try to connect those three pieces of information. Then to submit this, you're gonna render, just like I've been asking to do on previous assignments. And I'm asking you to all those warnings and directions for avoiding rendering issues are the same. Then after you render, you just add your last name to the file, to the HTML file, and then you submit that HTML on ELC. Initially, I had this due by Monday, but we changed that to be due by Wednesday, I think. Is that right? Is that right, Niva? So this is due by Wednesday, February 12th by 11:59 p.m. Also remember to add your name to the YAML. So your name here, make sure you change that. And that's it. All right, any questions about the assignments? All right, if you do not have a field, you can create a GitHub issue saying that you don't have a field, and maybe one of your classmates would have a, maybe somebody in class is working with more than one research field. They can give you the centroid coordinates of another field, not the one they're working on, but maybe a second field that they have research, and then you can get access like that way. But yeah, if you ask on GitHub and nobody gives you an answer, I'll share with you coordinates of another field that I have here, if needed. All right. With that, we finish this exercise and this exercise and the assignment introduction. We can close this RStudio window. Maybe we can take a quick break here just so you all can stretch a little bit. So let me give you 5 minutes for a quick break, and then when we come back, we're going to start working with EO monitor data. I'm going to be around, so if anyone has any questions, let me know and I can help you out. No worries. Yeah. So Aman, on the student side, can you see your submission? No. Can you show me how that looks like? And I think that may have been something I've done.
Try to look for a history, but
If you click on it,
social login.
okay.
I think when you send the afterwards, we didn't do one of the
Do you have anything else?
Otherwise, it will be showing
Yeah, so Eva, what I did one day was like you can basically import things from that class from 2 semesters. I think I may have imported the first time, and maybe I imported again after we had done the quizzes, and maybe that kind of like overrode. I think it could have been that, but I'm not sure.
because for other class it's showing this feedback. Like here for this class it's not showing any evaluation status.
Do you only have 3 quizzes as well?
Yeah, for this class only one. No, this is the 18.
Yeah.
For another we have limited quizzes. One. But no evaluation.
I'm not sure. I think I'll, because like when I maybe what I did was I copied the content from the previous year one time just for like quiz 1 and 2 maybe. And then I think I copied again for other quizzes, but I included 1 and 2 as well. So I think it may have overwritten. That could have been the cause.
It's due to both the things. But when we open it, it's showing completed.
Okay, let's try to look into that after class and see if there's a way to resolve that. Dun-dun-dun. All right. Let me see. I think Tifton people are not back yet. Maybe just Luke. All right, I see Polly coming in all right. Okay. So I think we're good to resume. Okay, so next exercise is going to be monitor data. What you can, so I just pushed to GitHub today a new partial script. So if you have not downloaded GitHub right before class, then you probably don't have the script that you need to have. So go ahead, download GitHub 2025 PPA. Inside of class code, there's going to be the 0206 EOD 17 wrangling partial. So let's just kind of walk through a little bit more slowly here. So go to GitHub, download the GitHub repo. Once it is in your computer, you can move that into your class folder. So the main class folder. So you're gonna see 2025 PPA main. Once you have it here, open 2025 PPA main, go on 04 class code. There is an EO17 wrangling partial script waiting for you there. Copy this script. And then go back to the class main folder. Create a new folder here called 07 underscore EO monitor. That's going to be our new working project folder. Once you create that, you can go inside 07 EO monitor, create code, data, and output subfolders. And then go inside of the code subfolder and paste the script. Oh, you know what? I just realized that let me check something. Yeah, so I just realized that I forgot to also update to GitHub the data set. So while you're doing all this setup, I'm gonna update the data set, and then unfortunately gonna have to download GitHub again just for the data set. So let me do that quickly here. So now if you go back to GitHub, I apologize for that. So GitHub 2025 PPA. Under this, the 03 folder, you're gonna have the EO data, the 07 EO data right there. I mean, you're gonna have to download the whole repo again. But once you do that, then the 07 EO 17 is gonna be there. And then you just also copy from 03 data, you copy that 07 EO 17 CSV to inside of your 07 EO monitor, inside of data. So in the end, your 07 EO monitor folder will look like this. Well, I have a complete version of the script. You don't have, but you should have the partial under code and the EO 17 CSV under data. And then as the last step for us to get set up, we're going to create that RStudio project. So open any RStudio window. Click, even if it opens a project that you already have open, like in my case, open 06 open data, just click on there, new project. Existing directory, you want to browse to that folder. So it's, if you remember now, it's called 07 EO monitor. That's the folder we want to be in. And then open a project right there. Create project, that's gonna launch it for you. Once it launches 07 EO monitor, on the files tab, we go under code, and then you can launch your partial code on the site, and we'll get started. So I know that we did a handful of steps. This is probably the 5th or 6th time that you are doing these steps. So I hope you're getting used to doing them. But just to make sure we're all on the same page, I want to give a quick second here. If anyone needs help, if anyone just need a little bit more time to catch up. All right. I'm gonna start moving here. If somebody needs more time, let me know. I can give you more time. But if I don't hear anything, I'm gonna start moving. All right, so with your EO monitor wrangling script open up here, let's begin this exercise. So the goals of this exercise here is gonna be to talk about the role of EO monitor data in agriculture. We're going to import one example of EO monitor data from a cotton field in South Georgia. We're going to explore this data here with tables, plots, and maps, what we call exploratory data analysis or EDA. And then we're going to learn and implement some data wrangling steps for geospatial data, right? So this is a precision ag class from the digitizing, or I guess since the NAS data that we started working with the spatial data, from now onwards, we only work with geospatial data. So, you know, some concepts here are going to be applied to any type of data, including geospatial, but others may be very specific to geospatial data, as you're going to see in this exercise. All right, I left you there the packages that we're going to need today. I think you have installed all of them already. So if you just hit the play button on this chunk, it shouldn't give you any errors or warnings. If it does give you some issue, you know how to install a package. So remember that on setup is where we have our packages and also where we bring in our data. So let's bring in this data here. If you know, just to inspect it on the Files tab inside of the data folder, there is a 07 EO17 CSV. So what function should we use to read this data into R?
read/CSV.
Okay, so Paulie said read underscore CSV. That's right. And Paulie, how do you know that it should be read CSV and not read SF?
Because of the type of the document we have is a CSV, that's the reason why I suggested CSV.
Awesome. Sounds great. So let me ask somebody else. What type of file would it have to be for us to use read SF? If you can give me one example.
A shapefile, for example, or any vector.
A shapefile. That's right, Benedetta. Thanks. So it could be a .shp. It could be a .geojson. Those would all require read SF. Because it's a CSV file, we're going to use a read CSV. Thanks, everyone. All right. So open and close quotation marks. We're just going to give the path, right? So / to get outside of the code folder. We navigate to inside the data folder. And if you just hit tab, it's going to autocomplete because there's only one file there. So if you run that, it's going to create this object for us. If we print EO17, it's going to tell us what's inside of this file. Okay, things that I always check for is number one, number of rows. This data set has 31,724 data rows. Each row is an yield point value on here that was collected by a yield monitor on this picker. We have 18 columns. So there's a lot of columns here, right? So FID, region, heading, elevation, distance, duration, speed, a lot of other things here. Mass of cotton, mass yield, wet yield, dry yield, and so on. A lot of stuff going on. And then it has a point X and point Y columns. Remember that as a CSV file, this is not a geospatial file yet, but it has geospatial information. That information is on point X and point Y columns. So we're going to use these columns here to turn this data frame into an SF object. All right, so we brought in the file, we checked number of rows, checked number of columns. Let's check the summary here of this data so we get some idea of how things are, what this data has. So heading is just the angle that the combine or that the picker was moving. So it just goes from 0 to 360 pretty much. Elevation here, I believe, is in feet. So 146 feet to 178 feet across the data that was collected from this field. Distance, duration, speed. This speed here is miles per hour. Fuel usage, the moisture, mass of cotton, the width of the combine, if it was engaged or not. Mass yield, so this is a good one. Well, perhaps not the best one for us to look at, but at least we don't want to see negative values because yield should never be negative. But this is not yield on an area basis yet. So we have mass yield, we have wet yield, and then we have dry yield. This dry yield is already on pounds of lint per acre. We're seeing here that the minimum is 0, so there is no negative value. That makes sense. The maximum is 4,275 pounds of lint per acre. If you don't work with cotton, or maybe if you don't work with cotton in Georgia specifically, so the average yield, cotton yield in the state of Georgia is almost 1,000 pounds of lint per acre. So the third quintile being 1,400 is not too bad, but this maximum value here, I don't know. It looks like a little bit too much for a field that the mean is at 1,000 and have a maximum of 4,000. So maybe this point of 4,000 may not be a very accurate data point.
Dr. Bastos.
Yes.
If it is data coming from the yield sensor in the cotton picker, I don't think that it is lint yield. It should be the cotton seed yield,
Yeah,
right?
so that's a good point, Marco. So on this case here, so I got this data frame actually from Dr. George Velides. He shared this with me. And I remember he was telling that some of these data sets he had already converted to lint yield.
Okay.
It's going to be one. So we're going to work with 3 years of data for this field, all cotton data. And there's, I believe, one of those years that it was still cotton seed or seed cotton weight. So that's a great point, especially for cotton. We have to be aware of that, right? Because the picker may give you here data on seed cotton yield, which is basically lint and seed together. And then we need to transform that to just lint yield, either by using data from this field or maybe by just simply using maybe data from the gin after it's ginned, or maybe just using a constant value that translates what you have. So the total amount of mass, which is fiber and seed, and then we have approximately 40% of that is going to be just fiber. That's a great point. Thanks, Marco. In this case here, I believe it's already just the lint yield, but yeah, especially in cotton, we have to keep an eye on that and make sure that's what we get. And if it is seed cotton yield, then we just have to translate that to lint yield. Okay. Yeah, thank you. Okay, so this exercise here, ideally, you would have done another assignment already, which you have not done, and I have not even given you that assignment. That is an assignment that you will do, however, in the future, related to yield monitor data and some of the errors that may exist in this type of data, and how we can try to fix those errors before we use this information for for research purposes, for management purposes, any way that you can use this data. But so even though you have not read that paper yet, I still want to ask you, what columns do you think are relevant for us to move forward in this analysis? Like we don't need all these columns. I can tell you that much for sure. But some of these columns are going to be really important for us, that we cannot leave them behind. Which ones would you say are really key for us to move forward? Okay, I'm on deep set dry yield. I agree. What else?
Speed.
Oh, sorry, go ahead.
Speed.
Speed, okay, speed is going to be important. And maybe this is one I was not expecting for you all to say, because you have not read that paper yet. But yeah, speed.
Moisture,
Yes, go ahead.
moisture data.
Moisture, okay. So the moisture data could be important if we did not have the dry yield. So this dry yield here has already incorporated the information of that wet of the wet yield and the moisture. But it could be important. In this case here, it's not, because it's already, so the moisture information has already been taken into account when calculating the dry yield here. But yeah, if this had not been done, then moisture would be required as well. What else?
The timestamp, point X and point Y, all three.
Okay, so point X and point Y for sure. And those are our coordinates. That's what's going to tell us where these points happen on the field. We really need point X and point Y. Timestamp, I mean, I don't think we're going to need for what we're doing. But, well, let me ask you, Kathy, how were you thinking of using the timestamp?
So it was mentioned in the paper, there is a function to remove the outliners if there is too much difference between the speed, if it's too fast, if there is too much difference between the time where the photo was taken and where the machine is. I don't know.
I see. That's a great point. I don't think that's, at least I have not seen the timestamp being used that way, at least in like row crop.
Uh-huh.
That's a great point, because maybe as you're saying, it would be important in other settings, right?
I think we used it in our own data once. So I just noted down the timestamp to know which sample is the picture taken
Mhm.
with by using the timestamp. So I thought it would be useful. Yeah.
Yeah, perfect. No, and really like, I mean, we're gonna select some of these columns to move forward. But perhaps there are others that could be also useful if you're applying different steps on the workflow. Right? So I mean, I'm not saying that what we're gonna select are the only ones important, but are the ones important for us in this exercise, right? So yeah. So similarly, when somebody mentioned moisture, moisture in this specific case here is not going to be required because we already have the dry yield column. But if you don't have the dry yield column calculated, moisture would also be important, right? So just wanted to let you know that we're going to make some choices, but this is not, it's not set in stone, right? There is different cases where perhaps you need more or less of those columns. All right, thanks everyone for all the help.
It's another question. You said we had another assignment. I'm not sure if it's isn't the one we submitted last night about the yield monitor, the
Yes.
yield data.
Okay, yes, sorry everyone. I'm teaching two courses this semester and my head is mixing things up. Yes, that was the assignment, Polly. Yes, thank you.
Okay.
Yeah, okay, so you already did that assignment. Great. So you know about yield errors and some of the sources of those yield errors, and that how we have to clean or remove those yield errors before we use the yield data to make sure we're using the best possible information. Perfect. Thanks, Polly, for reminding me. Okay, so let's explore this data a little bit. So the first thing that I want to explore is our response variable, is our variable of interest, which is dry yield. So the way I want to explore this is by using a density plot. So I already left part of the code for you there. We're starting with each plot. We have yield 17. On the X, I'm putting dry yield. You can add a plus there and let's call geom underscore density. So this creates a density plot for us. So this density plot is going to help us to visualize the statistical distribution, not the spatial distribution, the statistical distribution of yield data. And you can kind of think of this as as the outline of a histogram. That's in simpler terms, that's what a density plot is. So we see here that it looks like the peak of this density, which is at the mean. So the mean of this distribution is just above 1,000 pounds of lint per acre, which is what we already had some understanding of that from the summary function, right? So on the summary dry yield, the mean here is 1,150. That's approximately where it looks like this peak is. So just visually assessing. A couple of interesting features of this data as it is now, so the raw data. You see that, so if this was a full normal distribution, this tail would come down. However, this tail on the left is elevated, and that's because it has a lot of zero values and also really low yield values. Something else to also notice is it has a very long tail to the right. So there is at least one observation, perhaps more, that are pulling this distribution to the right. One way that we can check the density, so right now we're seeing the density of those data points, but we don't know where they're happening. So we can come here on the geom density. I want to introduce you to a new geom, which is called geom rug. So we can type plus geom underscore rug and run that. So geom rug pretty much puts a vertical little bar below the density plots everywhere there is an observation. It gets pretty busy because we have like 30 some thousand observations. So here is really hard to say what's going on, but it helps us to understand the tails especially, right? So we see here there is one data point that is past 4,000, which we already also knew from the summary function. There is a few data points that are between 3 and 4,000, and then maybe, more than just a few between 2,000 and 3,000. So this also gives us some indication or some understanding of the data distribution, how many points are pulling that tail out, and just the overall distribution. All right, so remember, yield is our response variable. So errors associated with yield could be many, right? As you saw, it could be so many different reasons. Now, if we go to the next chunk, I'm looking into a density plot of speed. So if we run this chunk and just let it print, this is how a speed looks like. So we see that for the most part, the highest peak here of speed is probably like 4.7, perhaps 4.8 maybe. If we go back to our summary function and look at speed, let's see, where was speed? We see the mean is a 4.67 miles per hour. So it's matching with what we're seeing here. That's great. However, it's a couple interesting things here. We see that to the left, so lower speeds, there is a long tail. Some speeds are even like close to 1 or even 1 mile per hour. This is very slow moving combine, right? And as you saw on the paper, if the combine is moving very slowly, or even when it's switching from slow to fast or fast to slow, we can introduce yield data errors. So what I want to tell you here is, on the yield side, some of these points here are probably erroneous and should be removed. On the speed side, it does not mean that the speed was erroneous and should be removed. It just means that under certain speeds, you're probably more likely to create yield errors, right? So there is a difference here between the yield that some points may have been created through errors, multiple errors as you observed. And speed is not that the speed is erroneous, it's just that under certain speed situations, that those situations may create erroneous yield data points, as we're seeing here. Another important thing to notice is on the yield distribution, we have the rug vertical bars pretty much anywhere, right? I mean, if you imagine here on this portion of the distribution, the yield is a continuous variable, right? So those rug vertical bars can appear anywhere in this spectrum here. For speed, even though speed is also a continuous variable, but the system on this picker that was taking note of the speed was doing that at decimal points, right? So it's either 4 or 4.1, 4.2, 4.3. There is no 4.15, or there is no 4.18, right? And this is just because of how the machine was taking note of the speed as it was moving. All right, any thoughts or questions about the speed statistical distribution or the yield statistical distribution? All right. So let's make a map. Let's make our first map here. So my goal is to show this data as a map. So now we're talking about spatial distribution of this data. I want to ask for help here. So let's start with ggplot. I want to say data equals to yield 17. Let's give it a comma. And I'm going to stop right here and ask you all to help me. What would you do next? It could be adding AES, it could be adding a geom. And if it is a geom, what would it be? Any guesses here?
We want a spatial distribution of yield, so probably a geom SF.
Okay, so Marco suggested GeoMSF. And Aman, you're gonna say something?
AES,
Okay, so we can use AES and then what?
then we can use E column if that satisfies everything.
Okay. All right, so I want to connect both of you guys. So Marco is saying let's try GeoMSF. Let's try that. So let's add a plus, break line, GeoMSF. And then Aman, you're saying on AES, what would you put here?
This is not spatial data.
Okay, so let me just repeat that online so others can hear. So Aman said, I think we should not do GeoMSF because this is not a spatial data yet. So what would you use? Okay, Aman is saying geom point. So maybe let's try GeoMSF just to see what happens. Okay, did not work. So it's saying here basically status F requires the following missing aesthetics, geometry. So it's telling us that it does not have a geometry column. If we print yield 17, it is just a data frame at this point. And even if we go all the way to the right, there's no geometry column. So I guess GeoMSF will not work in this case because this is not yet an SF object. It is at this point just a regular data frame that has two columns that are related to coordinates. So Amandeep was suggesting to do a geom point. Let's try that. Okay, that didn't work as well. But the reason is different. Now it did not work because it says it requires the aesthetics X and Y and could not find it. What would you do, Aman?
Yeah, we have to do AES,
Mhm.
then we just tell them like X equals to R, X column and Y column.
Okay, so Aman is saying we should say the X equals point X. So I'm just gonna print yield 17 here. X should be equals to point X and Y should be equal to point Y. Let's try that. Let's see if that works. No, not that.
Yeah, maybe.
Let's try. You know, it doesn't hurt trying, right? That's a lot of times we learn by trial and error. So X equals point X. I'm breaking line just to make it more readable. Y equals point Y. Let's try that. Okay. That kind of worked, right?
We get.
You didn't get it? You got go. So you gave me the right answer, but you're not sure how it worked. Okay, well let me tell you what's going on here. So right now, yield 17 is just a data frame, right? It's not an SF object yet. So GeoMSF will not work. However, it does have the coordinates, right? So if I say that this first point should be at this X coordinate and that Y coordinate, is just gonna find that space and put a point there and do that for every single point, right? So that's what's going on here. That's why it kind of looks like our field. You know, it's just not in the right orientation, or not. The X's are, as I was telling you earlier for geom stars, they're kind of distorted. We can fix that. So let's come here at a plus chord underscore equal. Let's just do that for now. And now it looks like our field, right? So something for you to notice here is an SF object, or even a stars object for raster, they have that geospatial information behind the scenes, right? It is there. It's just not obvious. There's no column with that information, but they're there. In this case here, it is just it is just a data frame in R. It's not an SF, it's not a stars object, but it does have those columns with the geospatial information of where the point is. So that's why this worked, and that's why it looks like what we think it should look like based on our field shape. No. So the field, each point has their own location. It's not just one point. So each one of the 37,000 points have their own location.
This is like raster, but
This is not raster, this is not vector. This is just a plot that we say what goes on X, what goes on Y, and it just puts a point in each one of those coordinates. That's all. So I think it's going to become maybe a little bit more obvious if we do a couple of things. So let's come here on geom point outside of the AES, or I'm sorry, not outside of the AES, inside the AES. Let's just color those points according to yield. So let's say color equals, the column name is uppercase D dry underscore uppercase Y yield. Okay, look at that. These are just points, right? We're just calling those points according to yield. Now, because those points are big in size, it kind of looks like that this map is continuous. It's really not. So for you to have an idea here, so a geom point will never be continuous, right? Because it is a point, it's not a continuous feature. So if we come out on geom point outside of AS, just say size equals to, let's try 1. Size equals 1. Okay, size equals 1. Well, is it size though? Let me try 0.5 and see if that changes. Yeah, so 0.5 is, I think it reduced a little bit the size. Let me try 0.1. You see, so the more we decrease the point size, perhaps the easier you start seeing some holes where we don't have data points. It's just that it is such a dense layer with 37,000 points or something like that, that it looks continuous. But if we were to zoom in, you would be able to see the space between the points at certain level, at some point. All right, so I know this was maybe a little bit confusing, this concept between, is it SF, is it raster? It's not, but we can make a map still. How come?
not a good question, but how big are every point?
Well, so Aman is asking, how did they get each data point? So this is basically a big machine, right? So it's a cotton picker that is harvesting cotton, and at a certain frequency is just dropping a point. It's collecting a GPS location of where it is and saying, this is how much yield happened here. And then it keeps moving. This is how much yield happened here. Keeps moving, right? That's what the monitor is doing. Yeah. It's harvesting, and it is assigning a geolocation for yield data at a given frequency as the picker moves through the field. Yeah, that's how, and yeah, this is not like a person with a GPS, right? This is like a machine doing that for you. All right, Marco, were you able to understand like why we did not use GeoMSF and how come geom point worked?
Yeah.
Okay, anyone else wants to discuss this or has any questions? All right, so let's keep moving here. I do want to tell you one thing though, which is that this, well, you know what, before I tell you that, let's come back to the chunk above. I want to change this to Virides again. So let's add a plus, scale underscore Virides. Wait, why is that not? Oh, sorry, scale color underscore Virides C for continuous. Let's just change that because I want to show you something. Okay, so now the color scale changed a little bit. There is, as we saw on the statistical distribution, there's one data point, or maybe three data points, only three data points in 37,000 that are above 3,000 pounds of lint per acre. Let's remove those, at least for now, just for visualization purposes, and see how the map looks like. So now that you change for Viridi's color scale, I want you to copy this code, paste below. We're gonna make a quick change here, which is gonna be, I want to remove the data equals yield 17 from inside ggplot. I want to come before ggplot, start off with yield 17, and I want to filter out points that are greater than 3,000. So let's give it a pipe called the filter function, dry yield. Well, I want to keep in what is less than 3,000. So dry yield less than 3,000. So this is going to remove a few points only, and then feed that back into that ggplot, and let's see what happens. Look at that. So I'll show you the code for just for a second here, and then look at that. Now that we removed a few very high outline points, the color scale range decreased, right? Because now instead of maximum being 4,000, now it's like 2,500. And then we can see more detail. So if you compare this one with this one, notice how much more detail you see on the second one, because we removed just 3 points that were skewing the color scale that we were be able to visualize. All right, I think this is a good stopping point. So I'm going to save this script here because we're going to 4:20 today. So we just have a couple more minutes. I saved this script. Let me open your attendance so you can claim your attendance. Right, I just opened the issue, so please feel free to claim your attendance. I do want to let you know that I'm going to look into what happened with the quizzes. On my side, I'm not seeing your submissions. If I cannot figure out, if I cannot find your submissions again, I'm just going to give everyone 100% on those quizzes. So you're not going to get penalized. And I'm not sure what happened there, but I'll try to figure out what it was so it doesn't happen again in the future. All right. Mm-hmm. All right, so I guess if you saved your script, if you responded to the GitHub issues claiming your attendance, then class is dismissed. But if anyone has any questions, I'll stick around for another couple of minutes and we can go over those.